Hello everyone, I'm Ikra Altaf Gilani and I'm here to present a paper titled A Group to Group Version of Random Walk Betweenness Centrality at CORD SCOMAT 2021. This is a joint work with Amitava Bagchi and Sayan Ranu at IIT Delhi. In this work, we are going to present a betweenness centrality measure. So let's start this talk by introducing centrality measures. Centrality measures are used to find the most important or influential nodes in a network. For example, they'll help you to find influential people in a social network, key infrastructure nodes in urban networks, or super spreaders of disease in case of infection network. Depending on what characterizes an important or influential node, different centrality measures have been proposed in the literature. There is closeness centrality, harmonic centrality, PageRank centrality, CAT centrality, betweenness centrality, and many more. In this work, our focus is on betweenness centrality, which was proposed by Anthonyse and Freeman. The betweenness centrality of a node measures the degree to which it lies on the shortest path between all other nodes. However, there are different types of information which do not follow the ideal shortest route, like news, rumor, infection, which just wander randomly over a network. So, to model the spread of such information, Newman and Brands proposed random walk betweenness centrality, which not only incorporates the contribution from the shortest path but from all possible paths. More formally, given an undirected graph G, the random walk betweenness centrality of a node V is defined as the expected number of visits to the vertex V by a random walk starting from node S and ending at node T, summed over all possible combinations of S and T over the entire vertex set V. So we can see here the focus is on all possible paths in the network. However, if we consider a special scenario as depicted by this network is of people interacting among themselves, and we consider an infected group of nodes is already known, which is marked here in red color, and our aim is to protect a group of vulnerable people like children or elderly from this infection. So we need to find a set of nodes which we can vaccinate so that this vulnerable group is protected from infection. In such scenarios, we extend the random walk betweenness centrality to a group to group random walk betweenness centrality. And this can be formally defined as follows. Given an undirected graph G, the group to group random walk betweenness centrality of a node V with respect to a source group S and a target group T is defined as the expected number of visits to vertex B by a random walk starting from node S and ending at node T, summed over all possible nodes in source set and all possible nodes in target set T. So we can see here again the focus is on all possible paths, but it's only from a specific source group to a specific target group. Now, to compute this expected number of visits term, we can go back to the electrical network analogy. That is, if we consider this undirected graph G as an electrical network where each edge is represented by a unit resistance, and we inject a unit current at the source node, which we extract at the sink node, then the current passing through each node in such a network is exactly equal to this expected number of visits to that vertex by the random walks starting at source node S and ending at the sink node T. So this means to compute these expected number of visit terms, we need to find such electrical flows. And in particular, since we need to do it for all possible source and target node combinations, we need to find the size of the source group times the size of the target group number of electrical flows for different source target pairs. There are different ways by which we can compute such electrical flows. Let's discuss one such way. Consider a graph G representing an electrical network with a source node S and a sink node T for an electrical flow. If we write the Kirchhoff equation of network, they can be expressed as a linear system Lx equal to B, where L is the Laplacian matrix of graph defined as D minus A, where D is the diagonal matrix of degrees and A is the usual adjacency matrix. X is the unknown vector of electric potentials and B is the special vector defined as follows. B of source is 1, B of sink node is -1, and B for all other nodes is 0. Under such a setting, the electrical flow along any edge UV is equal to XU minus XV. So to find electrical flow, one only needs to solve this Laplacian linear system. Now, if you recall, to compute our metric, we need to solve size of the source group times size of the target group number of electrical flows. So that many number of Laplacian systems we need to solve for our metric computation. However, we show an efficient method to find our proposed metric. For this, let's first consider the general Laplacian system of equations Lx equal to b. Since L is a singular matrix, with its null space being the subspace generated by all one's vector, we have that sum of all the entries of B vector should be equal to 0. And in general, this B vector can have multiple negative terms. However, the focus of our work will be on a special kind of Laplacian system, which we call as the one-sink Laplacian system. In such Laplacian systems, we consider a case where there is exactly one coordinate of B which is negative, and as a result, that coordinate is equal to negative times the sum of all other coordinates of the B vector. Moreover, since L is a symmetric matrix, we can rewrite the Laplacian system of equations Lx equal to B by taking transpose on both sides as x transpose L equal to B transpose. This form of the Laplacian system of equations will be useful for us as we'll see shortly. After defining the special Laplacian system in this form, we'll be expressing its solution in terms of the hitting time of random walks and relate it to our proposed metric. And that's how we'll propose an efficient computation of our metric. Let's have a look at the Laplacian random walk relation first. Given an undirected graph G and a source set S and a distinguished target node T, let P be the transition matrix of random walk on this graph. Then for the corresponding one-sink Laplacian system, which is eta transpose I minus P equal to B transpose, we obtain a non-negative eta solution, which is given as follows. We can see that this solution not only depends on the degree of the node, but also on some hitting time terms. So this way we relate the special Laplacian system with the random walk parameters. Now let's try to relate it to our proposed metric. From the random walk literature, it's well known that the expected number of visits to a vertex V of a random walk that began at vertex S before it hits the vertex T is given by these terms. And as you can see, this is exactly equal to our proposed metric term I subscript V of S of T. So if we rewrite the solution to this special Laplacian system in terms of these proposed metric terms, we have the sum over all possible nodes in source set, the expected number of visits to vertex V given the random walk starts from S and ends at T. And then using this eta notation, we can rewrite our metric as follows. So you can see here one summation of our proposed metric involving the sum over all nodes in the source set has been incorporated within the eta solution. This way, our computation of metric has reduced to solving the Laplacian equation only size of target group times, that is for different target nodes. Now, since our computation of metric involves repeated computation of Laplacian equation for different target pair nodes, we can further improve it by first sparsifying the graph, the best known algorithm by Chu et al., and then computing the Laplacian equation on the spacified graph using the available linear time solvers like that of King and Sachdeva. So our overall time will reduce to the following term. So this was all about our metric definition and its efficient computation. We also show experimentally that our proposed metric is effective in case of epidemic control scenarios. For this, we perform experiments on various real-world data sets. For regarding our experimental evaluation setup, we consider the infection spread model, that is SIR model, susceptible, infected, recovered model, and consider the following probability of infection based on the existing literature. So what we have is an infected group and a vulnerable group, which represent the source and target group respectively. And what we want is to rank all the other nodes in the network with respect to their importance in controlling the infection. And as a result, we can vaccinate them. We can obtain these rankings from different measures. First is our proposed group-to-group random walk betweenness. Second is our first baseline based on shortest path betweenness, wherein we consider the source group as one set and measure the number of shortest paths between the source set and a given target node that pass through the vertex V divided by total number of all such possible shortest paths. Our second shortest path baseline is much similar to our random walk betweenness definition. That is, it counts the number of shortest paths between the source node S, target node T that pass through the vertex V divided by all possible such shortest paths summed over all the nodes in source set and all the nodes in target set. Our last baseline is the PageRank centrality biased towards the source set S. We measure the efficacy of our measure by quantifying the total percentage of infected nodes of the target group after the termination of SIR model. Our first experiment is target group protection, where we want to protect a specific target group and we vary the vaccination budget from 10 to 60%. As we can see, as the vaccination budget is increased, the total infected percentage decreases. This is because as we vaccinate more and more nodes, have a better control at the infection. Across the data sets and across the different vaccination budgets, we can see that our metric performs better than other baselines for most of these cases. Especially, our performance is better at lower vaccination budgets, 10 to 30%. As the vaccination budget increases, we can see that the performance difference decreases. This is because at high vaccination budgets, different baselines tend to produce or choose similar nodes. In addition to varying the vaccination budget, we also analyze the performance by varying the source group size, target group size, and vulnerability percentage of target group with respect to the source group while keeping other metrics constant. Throughout these experiments, we see that our metric gives the best performance compared to other baselines for most of these cases. In particular, for the case where we vary the source group size, we see that the infected percentage also increases with the increasing source group size. This is intuitive because as and when we increase the size of the infected groups and given a fixed vaccination budget, the infected percentage will increase. Because given a fixed budget with an increased infected size, we cannot control the infection. Similarly, as the target group size increases, the infected percentage again increases because with a fixed vaccination budget, we will not be able to control the infection and protect a larger target group size. For the last case, where we vary the vulnerability percentage of target group, as this percentage increases, it's found that infected percentage decreases. This is because as the vulnerability percentage increases, we have a larger set from which we choose the target nodes randomly. So there's a possibility that we choose a less influential node as a target node. As a result, the overall infected percentage goes down. The second set of experiments that we perform is wherein we consider the target node set as the entire network except the source set. That is, our aim is to control the overall infection. Similar to the previous experiment, we see that for most of the cases, our metric performs better than the other baselines. For some cases where it's not the best, it's marginally differs from the best metric. We also perform this experiment on other data sets like US Airlines, Power Grid, and autonomous systems. But in the interest of time, we skip that because all those networks also show a similar trend. So this was all about our experiments. Now concluding the talk, in this work, we propose a group-to-group version of random walk betweenness centrality. We demonstrate a novel connection between Laplacian systems and random walks, which facilitates us to use Laplacian solvers for efficient computation of our metric. We also experimentally show that our proposed metric is more effective than other natural baselines for this problem for the epidemic control scenario. As part of the future work, we plan to extend the random walk-based centrality definition to group centrality setting, wherein we measure the centrality of group rather than the individual nodes. Under such a setting, our generalized group setting would be complete as we'll have source, target, as well as intermediate node all as group of nodes. That's it. Thank you for listening.